So let's look at the first thing that we were doing. So we have seen this following. This very elementary result already seen is the following. If you take your natural numbers and you invert them, that is, if you take these numbers and then add them, so you take 1, then you take 1 plus half, then you take 1 plus half plus 1/3, and you keep adding these numbers. So you can understand the pattern, obviously, like this. And just to be formal, we have hn equal to this, this expression. We are really trying to understand this expression. Okay, what happens to this? How big does it grow, or does it go beyond? So that is the analysis, the pure analysis side of it, or the pure mathematical analysis side of it, I mean, question. That question is or I'll just say, is hn bounded? Okay. What happens to this quantity? So what I'm saying is, what happens to this quantity when you keep adding more and more numbers? Does it become bigger and bigger than any number, or is it bounded above by some number? Is there some number such that it is always less than that? Okay, that was the first question. Okay, is hn bounded? So let me just give you a very quick small example where we came here from where. Okay, so just one small example is this very simple thing, which I'm sure all of you have know. If you take these numbers, now this is a part of this hn, right? It's a part, it's special numbers, and if you keep adding them, then I think all of you know this, that no matter how many of them you add, it's always going to be less than equal to 1, right? This is it's a common thing. If you don't know, just try to reason it out, or you just apply some formulas, but try to reason it out also, not just formula. So this we know, right? You keep adding infinitely many things, still it remains less than 1. So in that sense, it is bounded. The question here that we were asking is hn bounded? Okay, and the answer is no, hn is not bounded. So that's something that we have seen, and we'll obviously also prove it today in a different way from a more algorithmic point of view. But so the answer to this was no. No, hn is not bounded. Okay, it keeps becoming bigger and bigger than any number. We know this. So then the question is that the second important questions that come up is number theoretic question. Is this ever an integer? Is this ever an integer for any n? Is there an n for which this becomes an integer? It's obviously rational, but then, is this ever an integer? And other questions, number theoretic questions of that nature, which we are not going to look at today. So we looked at it a bit, but not today. So this I'm going to remove. That was the number theory aspect. But really, what we are trying to today understand is, what is the growth rate? I will explain these terms. Okay, what is the? But first, you can just already feel what I'm when I just put this colloquial phrase, right? What is the growth rate? Okay, the question here is, how fast does it grow? If you know that it grows bigger and bigger than any number, and we will see the reasoning for that for those who have not seen it, and we'll see it in a way that will answer the second question also. So that's the thing. But what is the growth rate? Okay, the question is that, see, why we are asking this question is, when you analyze a lot of algorithms, right, the steps, so you will see that at the steps you get half, then you get 1/3 bits used, and so on and so on. And so this kind of expression comes up in all sorts of places. Okay, this is also comes up in factorization of integers. So it has many sources. So this is the question. But the problem with this is that this is a very complicated function. That's the problem with this expression, right? When you input the number n and you get this very big expression, it's a very complicated. So we know that this is whatever that time the algorithm takes, or whatever process gave. No, zeta function is a generalization of this. Okay, but that's a different side of it. We don't need that right now. The point here is that this expression we can see, but we're trying to understand it. Can we understand it via a simpler function? Can we approximate this by a simpler function? Okay. Question is, can we approximate via a simpler function? Because it's so whose value we can easily calculate, okay? Because this is a complicated expression. We don't know what it's, how much roughly is it when n is equal to 1 million? What is a rough value? Do we know? We don't know, right? So this is the questions which we'll try to answer today. Okay. Let's first frame this as a problem, as a very simple problem. Okay. Let's frame it as a very simple problem. And this is a question which I had also asked in this one of the classes earlier, is after, and this is a very concrete question. Okay, this is a good way to start doing this. Start moving towards our approximation. Okay, after how many terms so this, I'm not expecting an exact answer, but roughly after how many terms does hn become bigger than some number? That number is not important. Let's say 100. You see, now this is a very concrete question. Now it's devoid from the sources. We have just made it very concrete. Okay. Yeah. How many terms do I need to add so that it becomes bigger than 100? You see, if we can answer this kind of question, then I can replace that 100 by other numbers and answer it again, right? And then you'll also get a proof of the fact that it becomes bigger and bigger than any number. So that will be proved, but we'll be proving much more. Okay, so let's think about this question. We can start thinking about this. After roughly how many terms, can you give an estimate? Does this become bigger than or equal to 100? So people can approach this from all sorts of places. Those, if you have done Euclidean algorithm, because that's where it comes from, one way, or you can just think about the basic grouping and comparing that is used here. Let's see. So roughly, how many terms do you think it will take, or at least give some n, which is a good n? Obviously, you can say 100 to the power 100, and that will be correct. But that's not a good, yeah. You can just say, just take 100 to the power 100, and you'll be pretty confident this works. But can we do better than that? Yeah. So this is a problem that has to be done. So you won't know the answer straight away unless you know some formula for it. Okay. So how to get started? Suppose this question comes up. How do you get started? Let's take some ideas. Let's just the starting ideas. If someone knows the answer, don't say the full answer. Okay. Just how to get started. That's right. Yes. So that's what we are trying to do. So that's right. We will compare, but not just compare, we will group and compare. So it's again the same, it's again the idea, group and compare, which is ubiquitous, just all over the place. Okay. Group and compare. Okay, now can anybody say more details as to how you think? That's right. No, but you see, this is this is a good start. The problem with this is, see, if you say less than, right? We don't want less than. This is right, and this is used in many places, kind of grouping, but not here, because we want a lower bound, right? We want it to become bigger than something. This will be useless in this situation. Yeah. So what kind of grouping should we use? Well, it's a very standard grouping. I think it's a very standard grouping, very simple one. Just the one that is used to is used in the standard proof of this. Okay, and there is the following. It's very basic. We basically are going to do following. So let me just write a few terms, and then you'll also get a hint. I think most of you know this, but it's just framing it might be a little. So very simple. You see, you see, we want a lower bound, not an upper bound. We want this to be bigger than something. What is it bigger than? The most obvious choice is 1 by 4, right? So we take the least member of that group, simple as that. It's just the basic thinking, right? Basic logic. So it's 1 by 4 plus 1 by 4. So basically this is half. Again, this is just the old technique that most of you would have seen. Okay, but here we are applying it to something to a more quantitative version of the question that was earlier asked, that is it infinite or finite? Okay, and we'll do more than that. We will we'll see. It's very interesting things happen. Then we'll take this group, and what bound should we put? Just simply 1 by 8. Perfect, right? So you see, and now I'll just condense things and just write half, because I think most of us are comfortable with this. So just write half, and you can understand. It's obvious now. It's bigger than half. Now tell me, how many terms would you roughly, according to this technique, how many terms would you roughly need to get to 100? Or what would be the last term? If you just think of it like that. What? No, 202. No, think. It's not 202. 200 is too less. No, it's not an AP. It's not an AP. It's more than that. It's getting see, the size of the groups are getting multiplied by 2, right? This had size 2. This has size 4. This has size, well, just a matter of calculation, but these are just some simple observations which you guys would make automatically if given more time. So that's not a problem. Right? This is just size 8, and similarly you can understand size 16, so on. Right? So now let's think. How many terms would we need? Let's further write this in a more suggestive way. So I'm just writing the size of the groups on the top. Okay, I'll just write here size of the group. This grouping technique is very far-reaching. Okay, we saw some condensation tests being developed from here, and we also saw some non-standard questions which you grouped up based on a different thing. So it's a very powerful and simple technique. So size of the group is 2. Size of the group is 2 square, 2 cube, 4, and so on. So how far do we have to go to get to 100? Yes, that's basically what this is. Yeah, but since it's just powers of 2s, we can even do this without using the word geometric progression, just so that we are more hands-on with what is happening. Okay, because it's just powers of 2s. That's a very simple case. So just use a pattern, right? So when you have 2 to the power 1, then it is 3 by 2, right? When it is 2 to the power 3, then by this time, let's just write half only. It's 1, I know, but let's just write half only for uniformity. Not an issue. So we have, you see, by the time you have 2 to the power 3, you have 1, 2, 3, 4, 5. And so when you have 2 to the power 4, you have 6. 1 minute. So roughly how many are you going to need? So roughly, I know, roughly it will be 2 to the power 200, right? I mean, the last group that you're going to look at will be 2 to the power 200, right? So you want a lot of halves. So here you want, how many halves do you want? You want 200 groups. right? You want 200 groups, and the 200th group size would be, well, what would be the size of the 200 group? Yes, or 2 to the power or 2 to the power 2 to the power 199, roughly like that, right? You can understand that. Yeah, so it will roughly be 2 to the power 200. Yeah, more or less. On the level of an approximation, you would have to go to 2 to the power 200, and this group half you have, and by this time you will have 200 halves, right? By this time you will have 200 halves, and so your sum would have become more than 100, right? 200 halves, so obviously more than 100. So 200 we need, so we need to go till 2 to the power 200. Okay, so what do we get? Essentially we get that if you go till 2 to the power 200 terms, then it becomes more than 100. Is this okay with everyone, or should I repeat something here? Yes, yes. So this is greater than half, greater than equal to half, and this is greater than equal to half. So yeah, or you can, even if you just forget about this, right? It's a rough approximation. Yeah, it's a rough approximation, you see, and this is better to just see it from here only, right? Because just to get 1, you have 2 to the power 2, right? To get 2, you have 2 to the power 4. So to get 100, you have 2 to the power 200. You see, it's just roughly the same thing. Yeah. First few terms you can ignore. Yeah. So this is what we get now. This is a bound. This is a nice bound, right? It also proves. So yeah, let's just write one thing in general, that h of 2 to the. Okay, sorry, just 1 second. I have to plug in the charger. Yes. So obviously we can write this general statement, that is 2 to the power h of 2 to the power n is going to be bigger than n, right? H of 2 to the power n is going to be bigger than n. Now, so we know that. So what can we say about the growth rate from here? Okay. So we know that if you go till 2 to the power n terms, then it will be more than n. Okay. This also means that, let's see. So if you're going till 2 to the power n terms, then it's bigger than n. So if you go till, let's say, m terms, then what can you say it is bigger than? Just a general m which is not of the form 2 to the power n. So basically we want to say something in general, right? Not just about powers of 2s. Yeah, so let's think about that. Yeah, so if you're going till m terms, some general m, then what can you say? It will be bigger than, right? And what can we clearly say? Yes, so it will roughly come in terms of log, in terms of logarithms, right? That's right. But just to say it in a more slightly more concrete way, though, yeah, log is the right thing, right? Notation is this. You see, if m is bigger than 2 to the power k, so if m is bigger than 2 to the power k, or even you could just say if m is between 2 to the power k and 2 to the power k plus 1. Obviously, m will be between two powers, right? And these are the motivations of how log comes, and you can understand digits and binary representations, number of digits, they're all related things here. And computers and algorithms, their notion of size of a number is the number of digits, and that's why A lot of algorithms have solutions as log n and n log n, and the depth of trees and graphs and all that. They're all have this log thing, but they usually don't come up directly as log as the answer. They'll come up in this kind of complicated expressions or some complicated recursions. So you can see where this is going. This will roughly be log n. Okay, but let's get there slowly. Let's get there gradually. So if m is bigger than 2 to the power k, right, and it is less than 2 to the power k plus 1, right, then you can just say that this is bigger than 2 to the power k, and this would be bigger than k. Right? That's what it is, right? Now, so what does if I say log m base 2, what does this mean? This basically means what power do you need to raise 2 to get m, and that power is roughly k. That right? That's what this means, right? What power do I need to raise 2 to get m? And I mean, yeah, then that's roughly k, right? And so you can just say this k is basically log m. Okay, so yes, that's exactly. Now, log m is a function that we can calculate by other means very quickly. So we will know, given our m, we will know how big roughly it will be. Okay. Any questions so far? No. Okay. So, yes. So you see, yeah. So basically, you see, we first ask the question that given a number, let's say 100, how many terms do we need? Right? Given a number 100, how many terms do we need to get there in this series? And we saw that, yeah, 2 to the power 100 terms are enough. And so in general, we have this. But you see, we set out with the initial goal. This was a concrete version, right? But we set out with the initial goal that we wanted to understand, given a m in general, how much it is approximately. Is that right? Yeah, given a general m, how much? Because I mean, usually that's how it might come. That's another way, right? So given a m, how big is hm approximately? So that was the goal, right? And so we know now, at least we have a lower bound. We know that given m, hm is at least this much. It's the same thing. We have not really done anything different from this. These two are just the same things. These two are just the same things, more or less. Okay. So what is the next thing that one should do from here? Well, we know that we have a lower bound, but is it a good lower bound or not is the question. Because you see, we have just made an approximation, right? We have just made an approximation. So we know that 2 to the power 100 terms will give you 100. But is that a good approximation, or is it, if it is something like 2 to the power 50 terms also? But so we know that we got this. But the question is this a good approximation? Okay. And the question is, I mean, if something like this happens, but this does not happen, we'll see. If this also happens, then our approximation is horrible. Right? So we want to show that it does not happen. We want to show that this is a good approximation. We want to show that this is a good approximation. So let's clear these things. And so we have so far, we have this. HM is roughly equal to this. Okay. Or if you want to keep it in the other form, you can just keep it in this form also. Both are the same things, more or less. The question now is that, is this a good approximation? Is this a good? Obviously, the good is, we'll have to define what that means. That is a question. Because if you're approximating by log m, but if it is actually log of square root of m, then your approximation is not good, right? Okay, square root of m would be fine, but because that's just half of it. But if it is some other function, completely different function, okay, then it's not. Or if it's like square root of log m, then it's not good. Then it's not a good approximation. So what does it mean? So we basically are trying to understand that when you look at HM and you look at this, so in the other way, this is how you can frame the question. When m becomes big, or for those who know the word limits, right? Roughly speaking, what we are talking about is when m becomes big, then what happens to this ratio? You see, HM on the top is a complicated function. It's a complicated quantity. And this denominator is, well, we can actually, at least we can calculate it simply, right? It's easily available thing to calculate. But the question is, what happens to this ratio? So if you call this some R of M, right? Then what is R of M? Or we are basically asking, is R of M finite at least? I would rather say, does the ratio remain finite? Does the ratio remain finite? I mean, we know that it's bigger than 1. That's what we have seen so far. We know that when you add up m terms, it will be at least, the sum will be at least log m base 2. Or if you add up 2 to the power n terms, then sum will be at least 10. Okay. So it's bigger than 1. Yeah. No, RM is just this RM is just for convenience. It's just this ratio. So you see, we know that HM is at least log m base 2, or if you add up to 2 to the power n terms, then you get at least n. But the next question we are trying to understand is that are these two things approximately the same when m becomes big, or does HM become very big again compared to log m? Okay. So that is a natural question. So we're basically trying to study this ratio and trying to understand what happens to this ratio. Okay. In other words, we are trying to understand if, see, we have this, but can we put an upper bound here also, which is in terms of log? You see, these are the similar kinds of question, right? They have put a lower bound in terms of log, but can you also put an upper bound? If you are able to put an upper bound, which is like maybe log m base 2 plus 1 or something like that, right? Then the ratio would be finite. Then as m becomes very big, this quantity hm would be roughly log m. Then we can say, right now we are not justified to say that. Right now, all we can say is that hm is at least log m. But if you can put an upper bound also, or in other words, if you can show that this ratio is less than some number, it might be a big number, let's say 100, though it is not, we'll see. Then we can at least say that these functions are roughly the same when m becomes big. Okay, these things lead to what we will do later in algorithms. It lead to the big O notation. Okay. And obviously in limits also, we use this all the time. In the calculation of limits, we approximate it by a power series or something. We replace it by simpler functions, right? So, and those are used all the times in proofs also, in complicated theorems in derivatives and so on. Yeah. No, there is there is no formula. There is no formula. There is a problem. There is no formula. There is no function that you can use to understand what is the sum of this. Okay. There is a thing, harmonic is a wavelengths that they come from the harmonics. No, there's no formula to add them. That's why we are doing so much. if we knew it, then we don't need to do anything. Okay. So yeah. So that is a question. Is there an upper bound? And the answer is yes. There is an upper bound again in terms of log. Okay. So let's see what that is. So till now we had a lower bound in terms of log, right? If you add 2 to the power n terms, then it is at least 10. Can we put an upper bound? put an upper bound on HM, or let's just say h of 2 to the power n. It is bigger than n, we know, but can we say it's less than something? And you see, once again, you can use the same technique of grouping and comparing, right? You can use the same technique of grouping and comparing, and you can get an upper bound. Just like someone was initially getting some sort of an upper bound, right? You can just do that. We will not execute that in the class today, but just the answer is yes. And it is just a similar technique. Just use the same technique of grouping and comparing, but do it with the upper bound. So just I will try to show the first few steps. One second. Okay. So how would you put an upper bound? So this goes on, but yeah. So you can just say that, look, this is less than half. And wait, no, this is less than, you could say it's less than half, but that will not be a good thing to say. 1 minute. So how would you put an upper bound? Let's think about that. All this can be done in other ways also, advanced methods, but we're just trying to do it so that we understand it. How can we put an upper bound? Yeah, I think we can just do this, right? So this is less than 1, right? And then again, this is again less than 1. So again, you can just write 1/4, 1/4, 1/4, and so on, right? Less than 1. And you see, you can just go in the same way. And once again, you can roughly say that this will be less than, this will be less than, I think, n plus 1 or something like that. Okay, just work it out. Just work it out and see what you will get. You will get something like this. Okay. And then we are done, right? Then we know that h2 to the power n, we know it's bigger than n. Please do this part, okay? And then you get this, okay? Which translates to, in the language of log, it translates to base 2. And I think, so I may be slightly off by a few numbers, but it will be roughly this. Here it is the reverse, but I'm not sure if in the sense in which you're saying. So earlier, you can just think of it in the following sense. If you had 2 to the power n given, then you can put a lower bound by grouping them in a way so that you put a lower bound, and then you can say it's bigger than at least n. Is that right? Now, given h of 2 to the power n only, because we have got a hang of the thing, we know that 2 to the power n is where where it is, right? Given a number n, 2 to the power n number of terms we need to check. We had arrived at 2 to the power n, but then you can look at the problem in the following way. If h of 2 to the power n was given, means 2 to the power n terms, then you can easily show it's bigger than or equal to n. We already showed that. But then you can group it in another way so that you put upper bounds. And then obviously this kind of grouping is useless to show that it's infinite. It will not work to show it's infinite, but it will be useful for us in this situation. In just the same 2 to the power n terms you can take, and you can put an upper bound like this. Again, just a similar technique. I've already started doing it here. You can check. So now I'm saying that I might be off by a few things, but you can just check it. Okay, that's not difficult. I think it's correct. Basically, it will be half the terms because we'll need half the terms, right? Because we are just kind of going faster. So roughly, this is what you will get. But from here, the best thing is that now we know that if you just divide by on all the sides, then you know that this ratio is roughly 1, or it may be half. I may be missing a few, like this may be 2 times this, but it will be finite. Okay, you can just fill in the details and see. Okay, so this is just approximately. So we have this, right? We have that HM is roughly equal to log M. Okay, that is what I wanted to show today. Okay. So it's not just a lower bound, it's also an upper bound. So it is roughly equal to log M. I mean, in fact, this can be seen in more cleaner ways by other methods like integration and so on. But right now, we will not get into that. I think this is more basic and easy to understand. Okay. So are there any questions so far? Okay. So we can say roughly that this is log m. That's, I mean, the base doesn't really matter. If you want to change it to e, then you will have to just divide by this, some formula of log, but you don't have to worry about that unless you need to in some problem. It's roughly this. Okay, this ratio is a finite thing. That is okay. So we will be using similar techniques. Okay, now the origin of the algorithms from which the different forms of log m comes through recurrences or through the series itself. So some algorithms, when you execute, you will get this series. And then to answer the running time, you will have to actually know this thing, or you have to prove it, or you have to get that in that situation. So those usually come from things like division algorithm and analyzing its running time, but that's a little premature for now, so I'm not doing it. It also comes through recurrence relations. Okay, so there are some recurrences where you have n steps. When run something in n steps, it takes 2 times n by 2 steps plus something like this. Again, those come from binary search and so on, which methods are also useful in calculus. So we will see all of them as time progresses. But right now, I'm just saying that this will be a very useful result. Okay. And we will also use similar approximation techniques later on to approximate. Again, this is again a complicated something which, you know, we do not, number theoretically, it's very nice number. It has a lot of prime factors. We know how to calculate and so on. But how much is it roughly? Can we say it in some known way? Yes. And so that also we will see using some known functions. And the technique will be similar. Put a lower bound, upper bound, and okay. But we will use integration here. Otherwise, I think it gets very complicated. So it finally just boils down to finding the area of something. So maybe I can just say that a little bit. When you're looking at basically some advanced techniques to calculate area, which is what integration is about, right, will also help you to make these approximations, is my point. So look, if you're adding up to n terms, and you can view this thing as the area of something, right? No, let's not go into that right now. I think that will take us on a different place. So yeah, let's not go there. So we know that Hn is infinite. We know it's a growth rate. Okay. Now I just want to explore something different, which is an alternate way, surprisingly algorithmic way, you could say, or whatever, an alternate way to show that Hn is infinite. Obviously, I mean, or rather I should say that Hn is unbounded. Hn is unbounded, meaning again the same thing as we know, it just becomes bigger and bigger. Given any t, it becomes bigger than t if you take enough terms. We just want to view an alternate way. Naturally, this can be proved. So if you are running an algorithm whose answer is Hn, okay, then obviously as n becomes bigger, you can, based on, you know, reasoning about the time and space, you can say from there also. But right now we don't have access to such algorithms, okay? But we will try to see it in a slightly different way, okay? Let's see. Let's just write Hn once again. Again, this, we'll just do parts of this and leave the rest for guys to try. This. Where have we seen this expression? Okay. So there was a problem that we had done, and it just connects with that also, where we had used greedy algorithms, where we had seen the following thing. Given a rational number, given it works for irrationals also, but for the time being, given a rational number, rationals will be enough for us. Given a rational number p by q, okay, you can write it using fractions of this type. Okay, given a rational number p by q, p by q can be written as yeah. So remember, the real demand of this is that all the ni's are different. That's really important. not just n1 not equal to n2, but all, yeah. This is from a series perspective, I don't think it's very interesting. Okay, but try proving this. Okay, the way to do this, so some of you have not seen the method, then it will be slightly difficult. Then you can just assume it for the time being. Okay, otherwise you can try proving it. Just try it once, then we'll discuss it in a different class. Given any rational number, it can be written like this, where all the ni's are different. Obviously, if you don't insist that all the ni's are different, and just then it's very simple, right? You could just take something like 30 by 17, then you can just write it as 1 by 17 plus 1 by 17 plus 1 by 17, and so on 30 times. And then there's nothing to do. But the real claim here is that all the ni's. So suppose you only had one copy of each fraction and you wanted to make. Okay, try proving this. The proof uses, if you know about this, the greedy algorithm. Okay, but otherwise you just think as a puzzle. It's just a question which you can just try it. Yeah. And for any rational number, this can be done. Okay, so this is a good question to try. Let's assume that we know how to do it. Okay, let's assume that we know how to do it. Can we use this result to show that Hn is unbounded? Can we use this? Yeah. So sorry, I meant unbounded. It's almost staring at us. Just think about it. Can we use this result? So assume that this is true. Assume that for any rational number, you can write it in this way. How can you use this to show that this series can become bigger and bigger? So see, it's almost obvious, right? Because I mean, let's say I want to make Hn bigger than. So this is an alternate way. Okay, we already have a way, but this we are trying to come at it from a different direction. Okay, I want to let's say I want to make Hn bigger than 200. But then I know, that 200 can be written like this. I don't know what those ni's are. I don't have a description, but I know it can be done because each step will be simple. Some sort of an algorithm we will have to devise to prove it. Or you can just try it. Just try it, take some numbers and try it, or just think how you can do it. I know that I can do this, right? So then obviously this is less than h of nk, isn't it? Because I mean, if this is n1 is less than n2 is less than nk, all are different. And let's say, obviously we can put this condition, right? So not equal, obviously. Right, so then nk is the biggest. So I mean, this is obviously going to be less than, it's going to be, it can be equal to, it will not be because, but in any case, it's true that it is less than or equal to, right? Any questions? Is this all right? Yeah, okay. So we know that this is true, right? So then we are done. Yeah, we are done. See, so this thing that we had done long time back, so this can be used here, okay, to show that it is infinite. But can anybody spot a problem here? And what is there any logical issue in what we have done so far? So what we have The way we have proved this HN is unbounded by assuming this result. What could we be doing wrong? Or no, it will not be, it will not be exactly equal to 200, right? No, see this quantity, let's take an example. Suppose just for a second, suppose that this is till 1 by 2 to the power 99, and then after that it could just skip things. It could skip, right? It could be 2 to the power 200. We don't know, right? Or it could be some other number, some 2 to the power 200 plus 75, 57, something like that. You see, it could skip things. So we have skipped things, right? So then this will be less than equal to h of 2 to the power 200 plus 57. So that is fine. It will not be equal. It may be, well, it will not be, but a priori it may be, and that's not a problem for us, right? But the problem is that when you try to prove this thing, you will use that HN is bounded. Sorry, it's unbounded. That is, so do you guys remember when we were trying to prove this, right, for a number 200, then we did use the fact that HN is unbounded. Okay, so that is where the problem is. So try proving it in a way that does not use it. Then only it will qualify as a proof. Okay, so this result you have to, yes? No, so yes, so that will really, for that I have to really go into the proof. Okay, so you try proving it, then so the way we proved it is like this, right? The way we proved this statement is like this, roughly speaking. You take, suppose you take the number 200 and you want to show that 200 can be written like this. Then the way we did this is we said, okay, this is one proof. You could do a different proof, and that's what we have to really come up with. Okay, you could take the number 200. We said, okay, take the number 200. Now we said, okay, take enough terms so that, so these are all consecutive, right? We said that take enough terms so that this 200 is bigger, but if you add even one more term, or I should say, yeah. So we're just trying to approximate. We said, look, take enough terms so that this is bigger than this. And if you add even one more term, then it becomes less. Yeah. Choose and so that. That's the natural, that's the usual way to approach this question. We said that, okay, 200 is a number I'm given. Now I have to use these 1 by n type of numbers, 1 by 2, 1 by 3, these type of numbers to make up 200. I will say, okay, as long as I can just add 1 by 2 plus 1 by 3 and so on, let me just keep doing it. And after that, I will think what happens, right? So in this, so going along that approach, right, we said, okay, let's keep adding just the harmonic series, 1 by 2, 1 by 3, 1 and so on. And till you are just behind 200. Okay, so just take the HN so that you're just behind 200, but the next one crosses over. Take that n. This is the first step that we had, that is usually done in the proof of this. This is again just an approximation technique, right? But how do we know that such an n exists? For that, we are using that HN is unbounded. After that, of course, there are a lot of other steps that one has to still think about, right? Then you have to take this and the difference, and that number you have to approximate. That number is going to be less than 1. It's going to be less than 1 by n plus 1, and that you have to approximate. And for that, you have to think how to do. For numbers less than 1, there is an easier way. But for numbers bigger than 1, like 200, if you want to write it using these fractions, you have to use the unboundedness. I mean, in the proof that we had seen, okay, along the lines of greedy algorithm. So one has to think of a different way to do it to succeed. Otherwise, this is what is a typical example of a circular error. Okay. So think about how you can do this. A hint is, okay, so any questions here so far? I just want to give a, how you can get started with this kind of question. So suppose you have the number p by q and you want to write it using fractions of this kind, but you don't want to use that hn is unbounded. You want to do it in a different way. Okay, then this is another approach which is again seen in greedy algorithms in general, is that you start with an arbitrary configuration and you improve it. You kind of add the improvements. So what we do here is you first start with this, which is wrong in the sense that this is not what we want, right? Finally, but we just start with this. We say, okay, fine. I do not know how to make them. I do not know how to write them as distinct sum. I'll just start with this. So this is just a way you could get started with an alternate way to prove this. Okay, to prove that this such an expansion exists. You say, okay, I'll just start with this. Let's see. Now I want to make these Qs all distinct somehow. Is that right? That's what we want to do. We want to show that I can make all the Qs distinct. So this is a different proof where you start with an arbitrary configuration and you make improvements. Okay. So usually, again, this is a very general principle. Greedy algorithms usually have these two things. Okay. One is that at each step you make the best choice, right? So for example, if you have the number 2 by 7, and if you want to do it by the greedy algorithm, you say, I'll take the best 1 by n, which works. That's just a rough thing. Okay, you have to fill in these details. Okay, try it. We'll discuss it formally. But if you do it by greedy algorithm, you will say, okay, I'll take the best 1 by n that I can take. And what will be the best one? 1/4, right? Because this is bigger than 1/4, and it is less than 1/3. So 1 by 4 is the best thing. And I'll subtract, and the smaller number, I will again try to approximate that. And you have to show that the algorithm terminates. You'll show that the process terminates, right? That was the way we did it, right? Make the best choices at each step. So this is one nature of greedy algorithms, right? At each step, you be greedy, you think locally and try to choose the best expression, the best possible choice you have, and then do it. And this is obviously widely applicable. Even this year's ISI question, first question was basically similar question. But the point is that is one approach of greedy algorithms. But dually, what from my experience I've seen is in approximation algorithm and other places, there's a slightly different approach. And sometimes only one of them are feasible. Okay. In this case, both are. The other approach is, especially whenever greedy algorithm works in one way, it usually works in this other way, which is, well, not usually, I should not use those words here. Just say that the other way is you start with an arbitrary configuration which matches some of your criteria, but not all of them. So you just start with arbitrary. So usually we say you start with endpoints, arbitrary endpoints. And then at each step, you make some improvements and you get to your result. That's the other way. Instead of starting with a point and looking at the closest neighbor and then checking, then doing something, that's the dual approach. So these are two dual approaches. Usually, if one of them works and the other would also work, and they both work. I mean, one of them at least works, and it's a greedy thing. So this is what this approach is about. I mean, I'll say these details more clearly, but the idea here is that P by Q start like this, and then you want to make these Qs distinct. Okay, how do you do that? You just think of some trick, some identity, and this trick is very simple. I mean, usually in a simple contest, maybe they will give you this trick, but in harder ones, they will not maybe. But the point is just that, look, you take this 1 by Q, you can somehow, some way, you can make these distinct. You can check this is true. Yeah. You see, now this is not yet done. You will have to still fill in a lot of details, okay? But this is the kind of a hint, okay? You can use this to make these things distinct, but then still there will be overlaps with other things or not. How you're going to do it, you have to think about it, okay? So this is just the hint to get started. Start with this and try to show that. Now, see, when you use this kind of technique, then you don't need to use that HN is infinite. You don't need to use that in this proof, okay? Think from here, okay? You can do it. Take a number, take the 7/3 or something, and then just do it like this. And try to make all the denominators distinct. This one, again, you have to do, but then again, if you do this, you will get the same thing, right? If you take, again, 1/q, but then the problem is, again, you will get this. How you have to think how you can make them all different. You have to think about that. It's not hard. It's just sort of an iteration. Think about it. So yeah, so that's for this section what I wanted to do. The next really was the what I wanted to do is the combinatorial nature of sequences and these kind of things. Okay, but I think we don't have time for that today. So I'll just quickly solve one of the questions which I had raised the last time. Okay. But this is just a problem for last time, but again, we can just all see this is very simple. We had seen the following thing, okay? So number one, we look at these numbers, A1, A2, A3, and you keep adding them. Right? And you're asking the question, is this finite? This is the fundamental question, right? Is this finite? In other words, rather to say it mathematically more correctly, it means that, is it true that for any n, adding up till n terms will be less than some number? That number will not depend on the n. Okay. So to put it here, is Sn less than some number m? Is there some m, fixed m universal such that all of these partial sums are less than that? This was the fundamental question, right? Obviously, for now, we take that they're all positive. We had seen that for if this is to happen, okay, if this is true, then we had seen that if this is true, then the terms, these an goes to 0. Again, we have not formally defined what this means, but for the time being, we're trying to get into approximations in combinatorial things, nature of things. So we're not define it concretely right now. We'll do that maybe a few classes. But this is roughly what this is, right? We know that this has to be true, and you guys can try to show that if the terms don't go to 0, like if they remain apart from 0 by some distance, then obviously there's no chance that this sum will be finite. That's an obvious thing. But the second thing is it true that A1 is bigger than A2 is big? That's very roughly putting. Is this necessary? Is it necessary that the terms should decrease? You see, that was the question that we were asking the last time. And obviously, this is not true. You can just change the first few terms. So this is a big no. And that's very, in a very uninteresting way, right? You can just change. So you can just take something like, so you know that if you take 1 square, 1/3 square, 1/4 square, by the way, you can show that this is finite. Just try again the same grouping technique, you can show that this is finite. This is roughly actually equal to pi²/6, but that is a very different thing from showing that it is finite. Okay. Is finite. So we know that this is finite. Okay. And you see it's decreasing. The terms are decreasing. And intuitively it feels like the terms should decrease. Maybe, but you can obviously put some spoilers. You can put some half, you can put some 1/100, and obviously it's not true now, and it's still finite. But that's okay. So then we change the question: is are the AIs eventually decreasing? Meaning this, what we mean by this is roughly speaking, because running time, roughly speaking, what this means is that is there a point after which they decrease, right? Again, try to write it mathematically, but is there a point after which? So we're trying to basically understand a series, adding these series via the terms themselves. What from the terms, what all can we say about the series? Right? And it turns out that we can say a lot, but that goes into more like analysis, which we're not trying to do in these few classes. Okay, at least for now, just for a couple of classes. After that, we'll switch back to hardcore. Is there a point after which they decrease. That is the question. So has anybody thought about this? So should there always be some term like, let's say one, that depends, 1 million term after which the terms have to decrease. Now, the sense was that this might be correct, because if you look at any series that any number of, if you look at infinitely many terms, you want to add them and you want to keep it finite, then it seems like the terms should decrease. But is this true, or are there some examples, counter examples? That's what we want to think about. And the answer is no, this is not true. Has anybody thought about counter examples? So see, this is very simple actually. So we know, I mean, for those who don't know many examples of series, well, it cannot actually happen that you don't know many examples, because we all know this example, for example, right? This is finite, it's just one, in fact. No, it's two because you've taken one, but in any case, you know it's finite, that's all that matters. Right, that's all that matters. And then you can just take this. You can take 1 by 3, 1 by 3 square, 1 by 3 to the power 4, and so on. And it's finite. You can calculate what it is, maybe. That's not important. The point is it is finite. That's clearly finite. And then how do you use these two? Just merge them. Just merge them. Right? It's a very, what I'm doing is, you see, it's a very silly question in the end, right? Because it was such a simple example. But yes, counter examples, one has to understand that it is really not decreasing, because you see what you can do is, you see it's big. Rather, I should maybe put 3, then you can put half, then you can put 3 square, then you can put half square, and so on. You see, there's always a zigzag. Right? There's always a climbing up, right? Because it's a very simple example, right? You guys should have thought about this, but in any case, it's very simple, nothing fancy. But it's just telling us that we shouldn't expect too much from these things, and these will be useful later on when we do asymptotes, and even in analysis algorithm, asymptotes, should an asymptote line be always decreasingly going there, and so on. It uses in a lot of places. But for the time being, this is simple example of it. Okay. Yes, so I think I have to stop because the time is way up. So, but yeah, next time we will look at combinatorial properties of these sequences. So we know that they don't have to eventually decrease, but we will show that we can find a decreasing part, and that there we will use the techniques of pigeonhole principle, discrete maths, so on. Okay, which we will use to show those things, that no matter how random your system is, there will be a monotonic thing in that. And that's for finite version. Also, there are results of that. Then we will see we'll apply the combinatorial methods to do those things. And yeah, then we will see how to branch out. Okay, today's class was in a unique position that it's both at the borderline of both, which can be used in discrete maths and in analysis. Okay, but that will not always be the case. So then we'll know. Any questions? Otherwise, class is over. So, yes. Where is the? Okay, it's not coming. Yeah, this one. No. This 2 is just if you add these things, it becomes 2. Because you can just say that, I think, yeah, this is 1. Actually, that actually doesn't matter what it is actually. It's just that it's finite is what matters. Okay. Yeah, both are finite and you can merge them. And this merging is very interesting. And in fact, we will see that merging is the best way to sort things. Okay, this merging technique. So because we had seen that sort when we're doing for those who were there, otherwise obviously we'll review it when we do it. When we're doing the interval scheduling, right, then we said that order it based on the finishing time and then select which one finishes first and blah, 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 right? But then how do you order in the best way? And it turns out that merging and first cutting it in between and then merging is the fastest way to do. And to prove what is that speed, we will need what we did in today's class, like this this harmonic, not harmonic, but the log thing that we got in the end. And this merging technique is the fastest. And to show that it is the fastest is a little difficult, but it's, yeah, we'll at least calculate its time and so on. So yeah, that's for today. Any questions? Anyone?